All right. So I have a couple of slides on the actual state of open source firmware right now. So how does the ecosystem look like? And what's going on? I don't know. Right? It's like a general overview on really what's the current status. The agenda is what is firmware in general. Maybe most of you know what firmware is, but just a small recap on that and why it actually matters. The whole firmware landscape, what projects are there, and what are they worked on, or what are they good for. The general vendor support status, a couple of deep dives into the projects, and then the industry trends and how the future maybe looks like. So what is firmware and why does it matter? So firmware is the critical layer that's between hardware and software, right? So without firmware, hardware is just a brick. So that means it doesn't work, right? Obviously, hardware is not as easy as that you can just put power on it and it just starts working magically. It has to go through some initialization actually to make it workable. And it's firmware is the abstraction layer between the operating system and hardware, right? So the OS cannot know each and every hardware and how to work with it, so there has to be some abstraction layer between the operating system and hardware, and that is normally firmware. Firmware is the most privileged code that is running on each and every system, so firmware can read and write everything, so every security mechanism that is actually out there can be circumvented if you own the firmware, or needs to be set up in firmware if it should be secure, right? And that means firmware obviously has a lot of implications on everything in terms of security, in terms of performance, like boot time, like PCIe, DDR and stuff, and also in terms of compatibility. So firmware is actually the thing that makes your system compatible with OS 1 or OS 2. Like, can it run Windows or not? It depends on what firmware you're running on the system. Actually, brings in the compatibility for that. So, what you would think how typical boot flow normally looks like is you got this wonderful power button that I designed, right? And you normally press it. And then after some time you're in the US, right? That's kind of the natural thing that you expect what happens if you use a computer. However, there's like much more going on when you actually start or any computer or any hardware, and this is like an incomplete list of stuff that you're doing, right? But you're doing, for sure, like memory training, right? You bring up all the links that you have, like PCIe. You have to initialize all the controllers that you have, USB controllers, PHY or Ethernet controllers, whatsoever. There's a bunch of stuff that needs to be generated for your hardware, like ACPI, some BIOS tables, and so on and so forth. If you're running on x86, system management modes needs to be set up. And all these kind of things you actually have to do, right? So firmware is vastly complex and needs to do a lot of stuff. That is also why we feel it's growing bigger and bigger, right? So because you're doing that stuff, and then what comes on top of that is, let's say, convenient features, right? So you want to maybe recover your system from the internet, or you want to, net boot something, or whatever, and that all comes on top of that functionality into your firmware stack. So it's actually growing by a lot and gets more complex. If you're looking at the host firmware specifically landscape, there's a bunch of projects that are actually there that you can work with, and I try to. So this is also an incomplete list, right? But I try to kind of make it visually seeable for you and divide it into client space, which is laptops and computers that you use as a personal device, server systems, right? And smaller embedded IoT devices that are actually out there. So Coreboot can be Coreboot is one of the main projects that we personally work with. Maybe you're not, right? That was the lie. That our company used to work with. And it runs on a lot of system. It has a couple of it doesn't really work on RISC-V server systems, but other than that, it actually runs on a lot of stuff. Tianocore is something that you might know. It's open source UFI firmware that is actually out there, and there are a couple of and that's kind of all standard stuff, right? I will go into them later again on deep diving into that. What's interesting is actually there's a lot of stuff going on the embedded ARM side, and actually that's a little bit incomplete because that also kind of accounts for RISC-V, right? So, client x86 client and server is kind of boring, right? You have like a handful of firmware projects that work there. But where it really gets fun is, embedded ARM stuff, for example, right? So you got stuff like Tamago or TinyGo, which is like bare metal Go implementations. You got a couple of Rust open source firmware stacks there. You got ARM trusted firmware. You got the Sapphire and FreeRTOS stuff that is actually there. So there's a lot of things going on there, which are quite nice and quite good and easy to play with. So if you want to divide that a little bit into categories on what is running on for what stacks, so host firmware, what we're mainly talking if we're talking about industry, what we're mainly doing there is core boot, it's EDK2, and it's U-boot, right? It's kind of the main targets that you have for host firmware, right? And host firmware is actually the BIOS that you know, right? So that's the stuff that brings up your x86, your host SoC. Server systems have something that is called a BMC, Baseboard Management Controller. We also have a couple of talks on that today, and there we have OpenBMC as the main prime target actually for open source firmware. Then there are a couple of smaller projects like UBMC or Canopy that are also BMC firmware, open source BMC firmware, but like the default standard right now is really OpenBMC. Embedded controllers are the ones in your laptop that do, keyboard backlight, that control your hands in your laptop and this kind of thing. There's more or less two main firmware stacks that we're using there, which is Sapphire and the Chrome EC firmware stack. Chrome EC firmware, I think, is also the one that Framework uses for their open source stack. And as I said right before, embedded IoT, there's like a vast minority of different firmware stacks that you can actually use there. Sapphire FreeRTOS are kind of standard. Tamago, TinyGo are Go-based, Go-based or Go bare metal projects. TalkOS and Hubris are Rust firmware. Hubris is something that was, TalkOS was something that started from Google, I think, and Hubris is something that is coming from Oxide computers, and then we had U-boot and a bunch of other stuff actually there. So if we're talking about open source firmware, we always have to kind of put that a little bit into perspective on what does open actually mean, right? So what you would think is that open source means it's open source, right? So it's fully open source. But that's actually not the case, and that's not even close to reality. So I got an example here for an Intel SoC, an AMD SoC, so that's both x86, right, and a Qualcomm SoC, and they all are used in Chromebooks, right? So I got that from a Chromebook presentation. And the green boxes are the open source parts, and the gray boxes are actually the closed source parts, right? So that these are binary blobs that are actually pulling in into your firmware stack, which you cannot read or write or whatever, right? So as you can see, depending on what architecture and SoC you have, there's a little bit more and less openness, let's say, in the stack. But in general, it's not great, right? So, and if you do the calculations, actually a little bit more than half of the stuff that you have in firmware is still closed source, right? And that is, if you're thinking about x86 SoCs, for example, right? Let's say Intel x86, you still got the ME firmware, like ME SPS firmware. like the management engine that is closed source. You got the firmware support packages that are closed source, and these are used for memory initialization or some parts of the silicon that gets initialized. You got like smaller bits like maybe firmware for your network card or whatever, right? So there are like smaller parts that are there as well. But in general, only, it depends on the platform, but plus minus half of it is actually still closed source, even if we call it open source firmware, right? So and there are a couple of changes on that. So this is like an older slide. So for AMD SOCs, especially on the server side, AMD is kind of replacing that part here. The AMD FSP was something that they call OpenSIL. So that one, goes away, let's say, or also becomes open source. But still, a lot of stuff still actually in closed source binaries here. So if we're coming to the vendor support part, so how does the x86 world look like, right? So x86 supports clients and client and server platforms actually. For Intel, so Intel started that what they called the firmware support package. There's a specification around that, and what they wanted to do is essentially protect their IP, right? So a couple of things that you actually do in firmware, these vendors tend to think that this is IP, this is special for them. So they wanted to protect that, but still wanted to enable the open source firmware communities. And they came up with the concept of the FSP, which is a binary blob, and it has a defined interface on how you call into it and how you pass data into the FSP and how you can get data out. And that was started on the client side first, right? So, and came into all the open source firmware projects. And a couple of years ago, that also started as a proof of concept on the server side. And I think nowadays is also pretty mature on the server side. It's not like the standard solution, and there are a couple of caveats around that, but still it's good for the community that we can actually get enabled through that FSP. AMD kind of adopted that spec, and they have something that they called Agesa, and they wrote a wrapper for that. So Agesa is also the part that actually initialized the silicon, and they wrote a wrapper around that, an FSP wrapper, so that they are compatible with any the Intel FSPs, right? So the idea was really that the open source firmware projects that are actually there do not have to do more work, but rather than instead of putting in the Intel FSP, they can put in the AMD FSP and also make it work, right? So they didn't want to force any new spec on the projects, so they adopted that. However, and that was going on for a couple of years now, and AMD, I think 2 or 3 years ago, they started this effort on OpenSIL, and OpenSIL is called, it's the short term for Open Silicon Initialization Library, and what they're actually doing is now, what they did in the FSP before, they are now opening that up and making that open source. They only do that for server systems now, and I think for next generation that becomes the standard solution. But I think right now it's still in proof of concept state. But you can actually fetch that from from GitHub, and they kind of publish every year or every half a year or something like that. They put a release out where you can get the new code. So servers are pretty good on AMD. On the client side, there was, or still is, actually strong support for FSP. They used to have that through Chromebooks, right? So everything that we do in open source firmware was kind of fueled by Chromebooks before, because every Chromebook is running open source firmware, if you didn't know. But there are no AMD Chromebooks anymore, So now AMD is doing a lot of in the automotive space with open source firmware. So that is good because like the new platforms still get support, but yeah, we're changing that a little bit. Right, and as I said before, right, there's like very strong support for OpenSil, through all the hyperscalers that are actually out there, and they are even replacing the proprietary solution with OpenSil from Venice onwards. So for ARM, that's a little bit more complicated because ARM is different to x86 in the sense of that ARM doesn't build socks, right? So there are a couple of ARM socks, but ARM itself doesn't build any socks. So the ecosystem is much more fragmented. So because there are tons of company out there, MediaTek, Qualcomm, Ampere, whatsoever, and they're all doing different socks and they can do whatever they want in firmware, right? So ARM has a specification on what they can do, but actually they are not bound to do any of that. And the open source support for all the different ARM socks are also pretty fragmented. So Qualcomm has something that they call QC-libs that is integrated into Coreboot, for example, to bring up the socks. MediaTek has also an FSP approach. Ampere has a different concept that they use ARM trusted firmware, and that is closed source. And I don't know how familiar you are with the ARM boot process, but at some point the ARM trusted firmware kind of gives over control to the untrusted firmware, and in the untrusted firmware part, you can actually run open source firmware, right? So, however, the system is more or less already up and running. But yeah, that's kind of the Ampere way on how they are actually doing it right now. So it's a vendor by vendor decision on if open source firmware is possible or not, and even if it works for one ARM system doesn't mean it works for any other ARM system. And yeah, U-boot is still the standard ARM open source firmware solution here. So I want to deep dive a little bit into different projects that are actually there that you can work with if you're looking into open source firmware. So one of the projects that is Coreboot, right? Coreboot has been around for decades. It's a minimal firmware that actually initializes the hardware. So the concept of Coreboot is that what we're doing in Coreboot is we're bringing up the hardware, so that everything works, and then we hand control over to something that we call a payload, which is essentially a bootloader, right? So what we don't have in Coreboot, for example, are drivers for to detect hard drives and these kind of things, right? So we cannot read hard drives or these kind of stuff because we don't want to, because we think the better way to do it is actually that we hand that over to a payload, and that payload then initialize your hard drives, checks what it can boot and kind of boots that then, right? It gives you the flexibility a little bit that it's a modular system, right? So you can bring up the hardware with Coreboot and then plunge in different payloads and different bootloaders for different use cases. Let's say you got a server system and you have it's very specialized and you only boot one operating system. You can run Coreboot plus Linux boot or Coreboot plus grub and then only boot Linux. But if you want to have like a general purpose server, you do Coreboot plus EDK2, right? So which is UFI, and then you can boot everything. So it gives you the flexibility, and you only have to do the Coreboot work once, and then for the payload, you can always swap it. It has probably maybe, as guessing, I guess it's true. It has probably the best x86 support for client and server systems. So Tianocore EDK2 is also pretty good, but Coreboot has a big and active community, so it's actually nice to work with that. And it gets adopted by the industry, by a couple of companies. So Chromebooks are actually working with Coreboot, right? So every Chromebook that you can buy is running Coreboot under the hood. There are a couple of other laptop vendors that are shipping Coreboot, Star Labs, System 76, Nova Customs, and there are probably more. that are actually doing that. You know, CSPs and hyperscalers partially adopt that, right? So ByteDance is running that in their infrastructure. Meta used to run that, and there are maybe more. And you know, then because of these companies actually doing it, a couple of ODMs and OEMs are kind of adopting it. You know, WeWin, Quanta, Mytek. They all have. They all work with Coreboot. They probably have, you know, proof of concept states and so on and so forth. So they are familiar with that. So Core EDK2 is a project that I mentioned quite a lot. It's an open source implementation of UFI. UFI is the standard firmware specification that is out there, right? So if any laptop that you boot, right, any server system that you boot, or majority of the systems that you boot, you actually need UFI because your operating system kind of expected to be there. So it's like the standard implementation. It's a complete UFI specification implementation. It has a rich feature set because it's used quite a lot. And you know, most OEMs and ODMs are kind of, you know, forking it and doing their own thing on top of that. So it's pretty mature in the sense of firmware. And it also works as a Coreboot payload, right? So as I said before, Coreboot has this concept of, you know, hardware initialization and payload. And you can actually run EDK2 as a payload and have like a UFI compliant system. And you know, startups and System76 and Nova Custom are actually doing exactly that. They have a Coreboot stack and EDK2 afterwards, so that you can boot, you know, Windows and everything. It's actually the reference implementation for AMD OpenSil, right? So AMD, with their OpenSil efforts, they are using EDK2 as a reference to implement that, and it supports, you know, client and server systems. And I think the last one that I have is that I want to touch base on is OpenBMC. So if you want to do open source firmware as a job, let's say, you know, OpenBMC is probably the best bet that you have right now. So it gets highly adopted. It becomes it's the de facto standard BMC firmware now. So every company that does server systems kind of looking into OpenBMC, see if they want to adopt it, if they want to build something with that. So it really gets a lot of traction right now. So if you, as I said, right, if you want to have a job there, I think you have a good chance on getting that. It's a Linux distro, right, more or less, right? So how it looks like is it's essentially a Yocto-based. It has a Yocto-based build system, and it builds together a complete Linux distro. Under the hood, it's U-boot and then kind of booting into Linux. A little bit complicated for me, but still kind of good. It manages the server hardware, so BMCs are essentially there that no one has to run to a server system and kind of plug, you know, a monitor in and a keyboard and kind of manage it by its own, but rather than you can manage it through a second processor or, you know, microcontroller who's on a server board. Then you can actually manage it remotely, right? So you can turn it on, off, can do firmware updates, can read all the sender data, so you can do monitoring and all these kind of things. Yeah, it uses Yocto as a build system and, you know, dbus as its internal communication, and you know, it provides a couple of REST APIs and so on and so forth, how we can actually talk to it, and also like a web UI. Yeah, it's standard for modern server systems. You know, most OEMs, ODMs kind of using it. They are most likely, you know, forking it and trying to build up their own value on that, and kind of tends to fragmentate the space a little bit because I think everyone tries to monetize that part right now because they want to add value on top of their OpenBMC stack and see that customer pay for that, or want at least differentiate there. So, but still, it gets highly adopted. You know, a couple of other projects. Linux boot. That's a Linux kernel in firmware, right? So that's actually a nice thing to have. So at some point we thought about why writing a new bootloader if you can just plunge Linux into your firmware and then, you know, kexec into whatever you have. So that's good. It cannot run on bare metal, right? So you have to have some firmware layer underneath it so that you can actually boot into Linux, and then Linux can do the rest. Tamago and also TinyGo are bare metal Go firmware implementations. So that's if you're in Go, right? That's also nice to use. U-boot obviously is like the dominant firmware for embedded ARM socks. So everything that is embedded in ARM is mostly running on U-boot. Sapphire is a real-time operating system for microcontrollers, so we use that for EC firmware, and you use that for IoT devices a lot. And Allboot, that's actually Rust-based firmware. So Allboot is coreboot without C, obviously, in the name and also in the technology. So that means, yeah, Rust-based, but it focuses purely, I think, on RISC-V, right? So it doesn't support any x86. There have been efforts that Allboot also runs on x86 systems, but the Allboot leadership kind of decided to kick all of that out and only use RISC-V systems. Yeah, industries, and I think I touched all of that more or less before. So OpenBMC is actually becoming, industry standard right now. Every hyperscaler that is actually out there, Meta, Microsoft, Google, and all of these companies that have like millions of servers adopting OpenBMC and are actually more or less only buying hardware that is running OpenBMC stacks. The smaller cloud providers, like the on-prem companies, are also adopting that right now. So if you only have a couple of tens of thousands of servers, you're still looking into OpenBMC. As I said before, there's a possibility of fragmentation on that because every OEM, ODM is kind of doing their own thing there. They're all using OpenBMC as a core and build up value on top of that. And not all of them are actually contributing back. So there's fragmentation happening there. For client embedded, Chromebooks are still like the main strong driver for client SOCs, especially for Intel SOCs right now. There are a couple of vendors that are actually using that. Framework doesn't use open source host firmware, right? They have like the open source EC stack that they have, but there's still no open source host firmware. When Daniel is here, you can actually ask him why not. Make a little bit pressure on them, and maybe they will get into that. And for a couple of security-focused applications that are also driving, open source firmware in the client space. Automotive, for example, is one of these things. Government is another thing that is really kind of fueling open source on client systems right now. So if you want to get involved into open source firmware, right, there's us, the Open Source Firmware Foundation, that you can check out. They have a couple of touch points where you can get involved into that. If you are working in the server space, OCP is a good place to be, right? The Open Compute Project. This is more or less the purchasing department of the hyperscalers, and they have like an open platform firmware group that actually cares about open source firmware. ARM has a couple of, EBBR and LBBR and SBBR and SBS and a couple of other letters that are, standards or specifications around firmware. So that's always a good thing if you're in ARM. And for RISC, they have this RISC-V RISE ecosystem that is actually pushing software in RISC-V, and that firmware is actually part of that as well. So yeah, to kind of summarize that, so open source firmware is production ready, right? So we're actually using that in production a lot. You might not always see it or know it or whatever, but it's really there and used on millions and millions of devices. There's strong support. For x86 for sure, ARM and RISC-V also, depending on what SOC vendor you're talking to, but still pretty good support. Community is growing because of the big tech companies that are involved now in open source firmware as well. So the hyperscalers, a lot of money is actually in that space now. So that means even the traditional IBVs are looking into open source firmware now. So that's great because that's more money, and the future is obviously open. So I put down that that presentation and the content of that presentation in the HackMD IO notes, right? These are always linked on the in the schedule, right? So if you click on the schedule and click on that session, you can actually find the notes. And I said before, I also auto-translated that with DeepL into Mandarin, so might be right or might not, right? So let's see. All right, that's all I have. Any questions on that? Yep. You want to have the mic?
You mentioned about the Chromebooks for ARM 86
Mm-hmm.
system. I'm wondering how the system for the Chromebook for ARM CPU side.
Yeah. So yeah. Your question was how is the ARM SOC support in Cobalt for Chromebooks? Yeah. So that's all there as well, right? So Chromebooks, also the ARM-based ones, normally use Cobalt as their firmware, right? So they have like MediaTek and Qualcomm SOCs, I think, that they're using, and that SOC support is also in Cobalt. Actually, you can find that there as well. So that is all there. Yep. All right.